Hi, I'm Jesse Silver, CFI candidate. Sometimes pilots and or turbulence can put too many G's on an aircraft, causing structural damage by being too forceful and abrupt on the flight controls. To protect from this, manufacturers publish something called design maneuvering speed, and by flying at or below this speed, the aircraft will stall before receiving any damage. Now, there are some caveats, namely, this speed changes with weight, and at first it can seem a little counterintuitive, but we're going to talk about the details here.
Maneuvering speed, VA, is the speed below which you can move a single flight control one time to its full deflection for one axis of airplane rotation only, pitch, roll, or yaw in smooth air without risk of damage to the airplane. In other words, VA helps protect aircraft from excessive G-forces from any single abrupt control input. It's generally based off the normal stalling speed, VS, at full forward CG. Now, there are various airspeed limitations for every aircraft. The Cessna 172 POH shows the upper and lower limits for the different operating ranges, and this is reflected on the airspeed indicator with the red line and the colored arcs. What's not indicated is maneuvering speed, and that's because it changes. Going back to the 172 POH, we see that maneuvering speed decreases as weight decreases. This is essentially because a lighter airplane flies at a lower angle of attack for any given speed and power setting, thus is further from its critical angle of attack, has a lower stall speed, therefore a lower maneuvering speed. Before going into that further, some fundamentals that need to be covered are the critical angle of attack, forces of flight, load factor, and the VG diagram. First, as the angle of attack increases, so does lift, up to the critical angle of attack, where a stall occurs. In most aircraft, this is between 16 to 20 degrees. At this point, the smooth airflow over top of the wing separates and becomes turbulent, and the production of lift falls off rapidly. Also, in steady, unaccelerated 1G flight, four forces are acting in equilibrium on the aircraft. Lift equals weight, and thrust equals drag. For any speed and power setting, a higher weight requires a higher angle of attack to maintain that steady, unaccelerated flight. Now, lift increases with an increase in angle of attack and at the same rate. When the pilot pulls back on the yoke, say to initiate a climb, it takes a moment for the flight path and relative wind to catch up and thereby the angle of attack to decrease and lift to re-equilibrate with weight. If the pilot yanks back on the yoke, lift will increase just as fast as the angle of attack until the critical angle, where the wing stalls, or structural damage occurs from excessive load factor or G-forces on the aircraft. Now, load factor is the ratio of lift to weight, and it's expressed or experienced in G-forces, and the load limit factor is the point at which structural damage occurs. The differentiating factor between when an aircraft either stalls or exceeds its load limit factor is maneuvering speed. That's demonstrated with a VG diagram, as shown here from the PHAC. It displays load factor versus airspeed vis-a-vis maneuvering speed. And it has the colored ranges showing what's on the airspeed indicator, and these positive load limits and negative load limits as specified by the airplane categories. The curved line here represents where the airplane stalls. It's the maximum lift capability. Now, there should ideally be a VG diagram for each aircraft, but Cessna doesn't publish one for the 172. So I've modified one to represent a 172 in the utility category with the appropriate airspeeds. So let's imagine a Cessna 172 in the utility category at its maximum weight for that category, 2,200 pounds, and a maneuvering speed of 98 knots. If it's flying along at that speed, 98 knots with 2,300 RPM, and say 4 degrees angle of attack to maintain that level of flight, if the pilot were to yank back on the yoke or the airplane experiences a large gust of wind from below and both the angle of attack and load factor go shooting up, they'll do so at the same rate. As we see here, it doubles and triples and quadruples, but the airplane will stall before reaching its load limit factor because it was flying at its maneuvering speed. By contrast, if we take a lighter plane, say 1,900 pounds, with a lower maneuvering speed as shown here, it's flying along at that previous faster speed of 98 knots, again, 2,300 RPM. Because it's a lighter airplane, it doesn't require as high of an angle of attack to maintain that level flight. So it's starting, say, at 3 degrees this time, and as the angle of attack and load factor goes shooting up, again at the same rate, it will reach its load limit factor before reaching its critical angle of attack because it was flying faster than its maneuvering speed, and it incurs structural damage before maybe eventually stalling. A scenario where this may occur is in a dive or recovery from one. If a pilot yanks back on the yoke, starting with that maybe relatively high airspeed and low angle of attack, the lift could drastically increase in relation to weight, and the load factor will go shooting up and could potentially exceed the G-force airframe limitations. Now, because we're never flying at those precise weights listed in the POH, we do have fuel burn after all. To determine our current maneuvering speed, we can use interpolation, we can use a formula, or just a rule of thumb. For every 10% weight decrease, VA decreases by 5%. And we can incorporate a margin of error by flying a few knots slower as a safety buffer. Some further considerations: as CG moves aft, the airplane experiences less total downforces, which means it flies at a lower angle of attack for any given speed and power setting, since it doesn't have to produce as much lift. So as the CG moves aft, maneuvering speed goes down. Also, it's best to avoid rapid and large alternating control inputs, especially in combination with large changes in pitch, roll, or yaw, for example in large side slope angles, as they may result in structural failures at any speed, including below maneuvering speed. To recap, for any given weight, there's an appropriate maneuvering speed. For any given speed and power setting, a lighter aircraft will require a lower angle of attack in stable flight. When the wing is further from its critical angle of attack, it is susceptible to higher load factors. Therefore, maneuvering speed will be lower as the aircraft decreases in weight.
So, if you're flying through turbulence, or expect to be, or you intend to be doing any maneuvers where you'll be loading up the wings with load factor and G's, remember to slow down to or maybe just below maneuvering speed to ensure the aircraft's safety and therefore your own.